The last time, on Monday, we discussed the properties of the gradient. If f is a differentiable function, then the gradient of f, if the gradient of f is the zero vector, then no matter what directional derivative we take, it will be zero. Okay, this later on will be known as a critical point. The second, which is similar to the third, are two very important properties of the gradient. The direction of maximum increase of any function of two variables is given by the gradient, and so that's what the gradient gives us. It always points in the direction of greatest increase of f. And what rate is it going at? The maximum value of that directional derivative is the length of the gradient vector. And similarly, the direction of minimum increase of f will be in the opposite direction, negative of gradient of f. And the rate, negative of the length of the gradient of f. Here is one example. Okay, we can use t of xy, this time instead of height, represent the temperature in Celsius on the surface of a metal plate. So you can see, you can guess from this function that at the origin, the temperature is the greatest. It will be about 20. And anything outside the origin will be less than 20. The further you go away from the origin, the colder it is. So this is the temperature function. So the question asks, for what direction must you move when you're already starting at 2 minus 3? Will the temperature increase most rapidly? And at that time, what is the rate of increase? We know that, so this is the level curve of the function t of xy equals 20 minus 4x squared minus y squared. At a point 2 minus 3, if we see this as a topographical map, we want to go, cross as many lines as possible to go to the highest temperature. But from what we know, the direction of maximum increase is given by the gradient. So if we calculate the gradient, and the gradient is given by negative 8x, that's from here, comma negative 2y, that's from here. Hence, therefore, the gradient of t at a point 2 minus 3 is negative 8 times 2, and negative 2 times negative 3, which is 6. So it's negative 16 plus 6. Negative 16 plus 6 is this direction. You can see it's not pointing towards the center. And at what rate would it be moving at? It will be moving at a rate of square root of this square, which is 256, and this square, which is 36. And that's the square root of 292. So this is the direction of greatest increase. So if we have to find the normal vector to a level curve, the best thing to do is find the gradient. So here is a function of two variables given by f of xy equals to y equals to y minus sine x. So the level curves are all sine curve. They're all sine curve being moved up and moved down. Yep. So if you have to find the normal vector to the level curve, then you find the gradient of this function. The level curve for 0 is just y equals sine x. So you find the gradient of this function, and the gradient of this function is given by negative cosine theta 1. Negative cosine theta 1. If we want to find where is the normal to the level curve, then at a point, say, minus pi 0, you see on the sine curve, minus pi is here, 0 is on this point. If you want to find this normal vector, then the gradient of the function we were talking about, you can substitute minus pi 0. So the gradient of the function, which is minus cosine x comma 1, you substitute minus pi for x and 0 for y, which, there's nothing to substitute for y. And the answer will be minus of minus 1, which is 1, and j is always 1. So the normal to this curve y equals to sine x will be 1, 1 at minus pi 0, as to be seen here. So if we go 1, 1, it will be normal to the tangent line. And there are a few calculations here that see what happened in other points. So this is another point. Here is minus pi minus 1, for example. Minus pi minus 1, this point here. It will be pointing upwards. You see, it's pointing just along j. So on and so forth. You can find, like, for example, 0, 0 will be pointing at minus 1, 1. So at 0, 0, the normal vector will be pointing at minus 1, 1. This is very, very important later on in the next section to try to calculate the tangent plane of function of the graph of a function. Yeah. And also the normal line.